All right, so in this video, we'll be covering your Lab 9B walkthrough. So let's get into it. In this lab, we're continuing the same skills as last lab, the test for proportions, and now we're modifying it to do, instead of one proportion, two proportions. So a lot of the same objectives. So here's kind of our setup here. And I'll use my pen to draw some of this out. So here's what we got. We have, in theory, we got two populations, population 1 and population 2. And to understand them, we're taking a sample 1 and a sample 2. And so we want to say, is there a difference between these? Are these samples the same? So we'll call this sample proportion. Again, we're sampling proportion, number of successes. We'll call that P1, and we'll call this one sample P2. And we want to know, how well do these represent the actual population parameters P1 and P2? And more so than that, we want to know, what is P1 minus P2? What's the difference of these proportions? And if the difference is 0, same thing, I'll get a better color here. If P1 minus P2 equals 0, that's the same thing as saying equals P2. That's the same thing as saying no difference. And that should sound familiar. No difference means that's our null hypothesis. So in a test, is there a difference? And the alternatives that will say yes, there is some kind of difference. So that's the underlying paradigm for this lab. And so I'll clear that. And in our studio, I'm using some fancy notation. Hat, backslash hat in parentheses allows me to put a little hat on my P1, backslash hat P2. And so these are our one setting to sample proportions. This should say sample proportions here without an error. So in the last time we were studying the sample proportions voting between Trump and Biden, rather than finding two separate intervals, we could compare these directly using some skills that we learned, that we will develop in this lab. So the question is, when can we apply our central limit theorem? In other words, when can we say our proportion difference that we're studying is nearly normal? So this will occur when the data within the two groups is independent and the data between the two groups are independent. So this is met if we're random sampling and then randomly placing them in two groups, or if they're two primarily different groups, randomly sampling from both groups, but independently. And the last thing is that we have to have our large enough sample size, our success failure conditions. So this would be at least 10 successes. Notice P1 times the proportion of success, N1 times the proportion of success is the number of successes. N1 times 1 minus the proportion of successes for sample 1 is also going to give the proportion of failures. So that's got to be greater than 10. And the same for our second sample. Okay. So then with that, we're going to use the pooled standard error. This is a different formula for standard error since we have two samples. Notice this should look the same, these two, but we're adding them together before taking the square root. So let's look at this. Here we go. We got two groups of people. Ages 18 to 24 and 25 to 32. We want to see, is there a difference between the voting proportions? Is one group more likely to vote than the other? So to check our samples, let's first look at proportionate success for group 1 would be 26% vote. And the proportionate success for group 2 is 29. Oh, sorry, that's the number of people in group 1, 100. And so we can check, do we have at least 10 successes and at least 10 failures? Yes, we do. We have 26 successes and 74 failures in that group. Then for the second group, we had a 29% voting rate out of 100. And so here's a bit of code that if you just want to remember that code and copy it, said 29 and 71. So we have a large enough sample size to test the difference in proportions. So let's calculate our standard error from above. So we got the square root of two different things, P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. So if we do that right, let's check what the standard error is, 0.063. So what this tells us is our sampling distribution, whatever it looks like, will have a standard deviation of 0.6311. So we'll go through how to find, if you look at the table of contents, confidence intervals and hypothesis testing for difference of proportions. So the first thing is a confidence interval. Notice before our confidence interval looked something like this. P hat plus or minus Z star, that's our critical value, times our standard error. That's what we were trying to estimate. But now, instead of estimating a single proportion, we're estimating the difference of proportions. So what's the difference between the two? And again, Z star is the critical value, SE we just found. So let's find out what the difference of proportions from the two data sets was. Here's again our data. We're finding the 95% confidence interval. I'm going to say P1 minus P2. That's the difference of the two proportions, like 26 and 29. So a 3% difference. And we're going to say plus 1.95, same critical value, and same standard error as we correctly found above. So if we do that, this tells us the right bound, we have to do plus or minus. Whoops. I'm using undo. So I have to say minus to get the two bounds. So this tells me negative 15.3. I want to make sure this is right. Percent, yeah, okay. Negative 15.3 to 0.93 to 9.3%. I could write it like that. Okay, so what does this mean? We got our confidence interval. What this means is that we're 95% confidence that the difference between the two portions is between negative 15 and 9. So this indicates that since 0 is in there, 0% would be no difference. And we're looking at, P1 minus P2 equals 0. That outcome is within our confidence interval. And what the confidence interval tells us is plausible values. So 0%, no difference, is plausible. It's possible that these samples are just the same, and statistically, the difference we're seeing is due to random error. So I could say any perceived difference in sample proportions may be due to randomness. So it's plausible that there is no difference. That's what the confidence interval tells us. So the big test is, here's the big question. Is your null value, in this case, P1 minus P2 equals 0, no difference, within your confidence interval? If it is, if the answer is yes, then we cannot reject null, because that value is plausible. If it's not, then we have evidence to reject null. So that's the thought process for evaluating our hypothesis. And remember, the null is no difference, meaning the two samples are the same. So let's go on now to doing the same, answering the same question, but using a p-value. So the p-value, since the first step of doing a hypothesis test is we assume null is true, where null is p1 minus p2 equals 0, no difference between the two. We're going to use that information in calculating our p-value. And so if we assume there's no difference, this means the proportions are the same from both samples. So I have to do something fancy called the pooled proportion. In calculating our standard error, we got to use this formula for finding out what the proportion is. And using that pooled proportion, we're going to find a slightly different standard error than we did before. So crazy formulas. You'll notice this is actually just a weighted sum, kind of like we did when we found the expected value. So let's find that for this sample. Okay, first, what are our hypotheses? So we're going to say there's no difference between the voting rate of the two groups. So in other words, P1 minus P2 is 0. And alternate would say, yes, there is a difference. P1 minus P2 is not 0. So let's go through all of our steps. Oh, I skipped step 4. Let's find the pool proportion here. P1 times N1 plus P2 times N2 divided by N1 plus N2. That's my pool proportion here. Yep. So I'm going to put that here, and you can check that. 27.5% of people voted total. What this means is out of the total group, 27.5 people voted, which you notice since there's equal size groups, it's just the average of the two groups. That helps to think about it that way. Now let's find our pooled standard error. So we got PP times, what's the formula? Oh yeah. Pool proportion times 1 minus the pool proportion divided by N1. And then I'm going to do the same thing, but divided by N2. So there's my standard error. So let's look what all this means. Here we go. So since we assume the null is true, we're assuming the middle of my distribution is 0. This is the distribution for P1 minus P2. We're assuming it's 0. We got a standard error of 0.063. And what now did we observe? So the second step was plot the distribution that results from assuming that, your sampling distribution. And 3, where's our data? Where does the data lie on a distribution? Just like before, we have to put where this data lies. So we observed, what was it, a negative 3% difference? So that would be to the left of the mean. And so where does the data lie on the distribution? Use that to find the p-value. Okay, so finding the p-value is the chance of observing something more extreme than what we observed from our data. So something more extreme would be away from the mean. Oops, I lost my annotations. So it would be like this side. And since we're interested in the alternative hypothesis being P1 minus P2 is not equal, that means we don't care. It could be less or it could be greater. So we have to go the equivalent distance Place that here to the right, 0.03. So we want to find out the area of both those tails. Okay, so now we can bust out p-norm for all that work. So p-norm, I'm going to do the lower tail first, negative 0.03, with the zero mean, and standard error was SE. Put this in here just to be clear. So if I run that, that's the area of this little tail here. Okay, and we want to find both tails. Because this is symmetrical, we can find the area of both tails by multiplying by 2. So that tells us our p-value. 6, 3, 7, okay, 65. So now based off that, I'm all over the place. Calculate the standard error. Okay, I was ahead of myself here. So this is just the standard error. I calculated that for 4. Number 6 is calculating the p-value. So that's what I did. I found the p-value to be 63.0635. And so now we're going to sing the song that I'm teaching you in class. Since the p-value is bigger than significance, we want to compare that p-value with a significance, which I think we use 95%, so our significance is 5. So if our p-value is bigger than our significance, if the answer is yes, we fail to reject null. The answer is no, we reject the null. If it's smaller than the significance, we reject the null. So since it's bigger since this value here, our p-value is pretty big, we have to fail to reject the null. So we really have no conclusion to this test. Since it's bigger, yes, we fail to reject the null. This means there is no conclusive difference. Or more accurately, I could say no statistically significant. Between my two samples. Okay, so that's the test. That's a result. And it matches what we found earlier. Remember we found from our interval, there was no perceived difference. Anything that's perceived to be different is due to chance. So we get the same result, depending on whether we use a confidence interval or a null hypothesis. Okay, so you probably have some questions, bring them to class. And then the next 2 examples are ways you can practice doing all this. And we might go through one of these in class together. So I hope that helps, and keep with it, stick with it. Look at these examples, go through them, and you'll get better and better. And with these examples, you can check your work in the back of the book. So everything that you do here, you can make sure you got the right answers just by looking at the results. Okay, so that's all. We'll see you next video.